So we got these up and running, got these. Okay, so here's what we have, Adam, my friend, for you. We have typically, you can have a picture of this. Typical a transformer panel that you can have in every commercial industrial building. It's always starts with a high voltage. HP is a high voltage panel. It's always 480, right? Through a circuit breaker and a feeder, it will be feeding a transformer, XFR. From the transformer, we'll be feeding 280, 120, so we can get our receptacles, 120 receptacles, and lights, if any. Typically, lights, guys, in a commercial building, we burn them at 277. The only thing different that we need is 280, 120 for receptacles. Okay. So here's what. So this is how physically it's going to look like, physical location. This is how the graphic is, a one-line diagram of it. So we start with the overcurrent protection device, guys, on the primary side. That's the primary feeders, the transformer itself. Then we're going to go into the feeder that feeds the secondary side, the overcurrent protection device, and the panel size. Any question is on what we're trying to achieve here? So what we're trying to achieve first, as you have a load for receptacle load, guys, right? Here's what we have. I have an example based on we have receptacles. Whom am I going to pick on? Kerry installed 200 receptacles in his building. Multi-outlet assembly installed 60, and continuous one and non-continuous one installed 70. And we're supposed to size a receptacle panel and a receptacle transformer and size the feeders and overcurrent protection device for all of them. Any comments, any questions, what we're trying to achieve? So what I'm hoping is this will help you, Jeff, design your system. When you do the riser right now, when I redline the riser for you, I'm going to ask you what size transformer did you come up for the receptacle panel? What size transformer did you come up for the 280, 120 bus duct? The example that we have in our project, guys, are two, as a matter of fact. One is for the 280, 120 bus duct, and the other one is for the 280, 120 receptacle panel. Okay. And then from here, we take a branch circuit and we feed receptacles. Typically, guys, if you have a commercial industrial building with 480, 277, typically, Joe, my friend, lights, everything will be burning at 277 and 480, equipment and lights, and the only thing that you will be burning at 120 is receptacles, right? Any comments, guys, why this is so important in any commercial industrial building that you enter? When we went to Boston Scientific, did you guys see the transformer? Joe, you and I were looking at it, right? There was a big panel, a transformer on the floor, feeding another panel. That's exactly, how do you size this system? That's exactly what we're doing. Any comments, any questions about what we're trying to achieve? This is a receptacle panel. We're not adding lights to it. Good point. LP is, this is my LP here is actually a low voltage panel. Let me clarify these, and I know LP we've been using it for lighting panel. Let me clarify the H and the P. Typically, guys, in the industry, when they use the word the HP for the high voltage and LP for the low voltage. Okay, I know we use it for lighting panel, so everybody's aware of that. Why I use this example for all practical reasons. You can call this one, I don't know, main panel, and this one receptacle panel, or P1 and P2. Everybody understand that? But the H stands for the high and the L stands for low. And just to indicate that we have a high voltage here and a low voltage, two different voltage systems. Any question, guys, about two things? Number one, what we're trying to achieve, and number two, the importance of what we're trying to achieve. Cool? Everybody's okay with that? So, based on the load, we need here's what I'm giving you. I'm giving you 200 receptacles that you guys have thrown in that building with multi-element assembly continuous and non-continuous feeds. Now we need to go and size a transformer. So first step in a system like this, Joe and Jeff, is go size a transformer, which is number one, here and here. Second, we're going to go size the overcurrent protection device on the primary side of the transformer. Third, the feeder on the primary side of the transformer. Fourth, we're going to go and size the, where's my point? The panel itself, the low voltage panel, the 280, 120 panel. Fifth, we're going to size the overcurrent protection device that will protect this panel, either inside it or outside it. And 6, what we're going to do, guys, is we're going to size the feeder on the secondary side of the transformer, which in reality will be where? It will be also feeding the receptacle panel. Can you guys see that number 6 is actually the secondary feeder of the transformer, and at the same time, the feeder that feeds the panel? Everybody can see that? What's unique about this? We already did transformer, guys. What's unique about this? We did panels and we did transformers. The unique thing about this example is putting the two together. Putting the two together. Any comments, any questions? Everybody understand what we're trying to achieve? Shall we go achieve it? Cool? All right, so the goal again is to put your receptacles and feed them. So let's go ahead and start. The first thing I would like to add, guys, and I do have my solutions here, so it'll help a little bit. Let's use, which color am I going to use this time? Let's use a different color. I'll use green. So, transformer sizing. I'll give you a few seconds to write. If you guys go to 220.14H, 220.14I, it will tell you these two articles, transformer size, when we size it, you take the number of receptacles and you multiply that number of receptacles. The number of receptacles was 200. Multiply this one by 180. Where would that tell you? If you guys go to the code, I believe it's 220.14H. It will tell you, and we did that one, and you guys did it with me for the load calculation. So we have no interest in doing the load calculation again. This is just for your reference. 220.14H. This is for multi-out assembly, and I believe is for receptacle outlets, 180. Receptacle outlets, 180. Okay. So where did I get the 180, guys? From on. Everybody can see that? Everybody can see that? Okay, so for multi-outlet assembly continuous, multi-outlet assembly non-continuous. Receptacle, multi-outlet assembly continuous, multi-outlet assembly non-continuous. Okay, any question about 180? Piece of cake. So let's go to the multi-outlet assembly continuous. We have 60 of them. Multiply by, if they're continuous, guys, you give everyone 60 feet. You give every, for multi-outlet assembly, for every 1 foot, you give it 180. Are you okay, Darren? Lost your notebook? Ouch. Okay, 60 multi-outlet assembly feet. This is my 60 feet, and then multi-outlet assembly non-continuous 60. The same thing multiplied by 180. The only thing, guys, if they're non-continuous, when dividing by code, you divide it by 5. For every 5 feet, remember that? For every 5 feet, they give you 180. The non-continuous is 70. Thank you, sir. The non-continuous is 70. Thanks. 7-5. So it's not about 5. Okay. So you add them up. Here's what you're going to do. You're going to add all these up. And when you are set and done, you're going to end up with 49.3 kVA. 49.3 kVA. Mistake number 1 is people put them, don't know how to get the K, right? How do you get a K? You divide everything by 1,000. When you size transformers, guys, you talk K. Power transformers are not volt-amp, they are kilovolt. That's why I divided directly to K, and now you guys are good to go with that. Any questions guys about this? Doesn't matter. The same answer. Typically, it's 70 divided by 5. Yeah. If you multiply 70 by 180 divided by 5, it's the same as taking the 70. But typically, it's this way here. Right? There's brackets here. Any questions about this? You guys have done this in your load calc with me. You have done this multi-outlet assembly. You design it in Excel. Nothing new. Okay. Any comments? Any questions? Now, Jeff, since these are receptacles in a commercial building, we need to go to rate them, right? So if you guys go to table 220.44, 220.44 talks about receptacles. 220.44 talks about receptacles in a commercial building. Receptacles in a commercial building, the first 10K are sacred cow, leave them alone. Anything higher than 10, what do you do with them? Anybody remember, Aaron? What do you do with the anything higher than 10K? Cut it by 0.5. Cut it by half. After 10K, you cut it by half. You guys did that one with lookout. Okay, so let's go and take this 49. I have my 49, 49.3 kVA. Okay, the first 10K, what do you do with them? Leave it alone, kVA. Then anything higher than 10 kVA, which is 49.3 minus 10. What do you do with these, my friends? Multiply it by 0.5. And what do you do with the total? You total them to, and you end up with 29.6 kVA. 29.6 kVA. You end up with 29.6 kVA. Do not forget to add them up. Don't forget to add them up, guys, here. Don't forget to add them up. That's called demanding the receptacle load. You guys have done that? Demanding the receptacle load. Demanding the receptacle load. Now, who said about lighting? Aaron, if there's lighting load in this transformer, you add the lighting load at 125% right to this number. But we're assuming if you guys have a receptacle panel, Jeff, in a building that has 48077, you won't feed lights from a receptacle panel, right? Guys, separation of functions, so you know it's easy for maintenance, troubleshooting that we have your receptacle panels, control the receptacles, so you don't want to go accidentally turn the circuit breaker off and that will turn the light, not the receptacles and so forth. So it's a good practice. Any question, guys? Am I going too fast, too slow? Okay. Grab your DeWalt, will you? And go to 7-7. Very important page in DeWalt 7-7. Page 7-7 DeWalt. Now, Jeff, when we size transformers, we size based on industry standards, not based on what we like it. I have 29.6 kVA. Either I have to call Square D and ask them for custom design at 29.6 kVA for me. Well, guess what? I'm going to be using the standard industry standards. Why do we care about industry standards? Because that's what the electrical contractors will be buying to install, guys. That's what you're going to be installing, actual equipment. Okay, do me a favor. 7-7 DeWalt. Everybody's there? 7-7 DeWalt. If you guys look at the page, it's a three-phase full load current. I would like you guys to look at the following. Can you look at the 100 kVA first? 100 kVA. Okay, 100 kVA. If the primary is 208, what's the full load current? Joe? 277.6. If the primary or the secondary, it doesn't really matter. The primary or the secondary is 240. What's the full load current? Thank you. If the primary or the secondary is 480, what's the full load current? 120.3. If the primary or the secondary is 240 volt, 2400, 24. If the primary or the secondary is 4160, 13.9. What they did here, guys, in this table, two things. They gave you the kVA size of the transformers, as well as the full load current at certain voltages. So, Zach, does it matter if these voltages are primary or secondary? It doesn't really matter. Okay? In our case, guys, and 99% of the time, what are you going to be? You're going to be primary 480 and secondary 280. Okay. So let's go size my transformer, my friends. So the transformer that we're going to be taking, where's my transformer that we're going to be taking? We're going to be taking 29.6 kVA. Take it to DeWalt 7-7. What's the next standard, Jeff? And you go to kVA. We're looking at kVA, not full load there. So I have 29. So we hit the jackpot, and we have 30. So we're not far away. We are looking at 30 kVA. So what's the size of my transformer? What's the size of my transformer, guys? The size of my transformer is 30. The size of my transformer is 30. Now from the get-go, if you guys go to the same table will give you two full load currents. We're going to calculate them anyway. It will give you at a voltage of 480, Jeff. What was the full load current for that particular transformer? Right from the table at 480. 36.1. Thank you. 36.1 amp at 208 volts. Right from the same table. What's the full load current? 83.3 amps. Directly from the table, guys. Everybody can see that? Everybody can see that? Directly from the table. So I can get the full load amp. We're going to calculate it anyway, but we're going to check if these numbers are right. So directly from the table, I sized the transformer size is 30 kVA, and on the primary side, the table will give you 36.1 amp. On the secondary, give you 83.3 amps. No rocket science. What they did, Andrew, is they took the kVA divided by the voltage and 1.73. That's all. Really not. They calculated it for you. Okay. So highlight the 30 kVA. When I was correcting the test for you guys, when I gave you wrong, if you put the bus duct size 930 amp, the bus duct size. That's not the bus duct size. The bus duct size, you have to go to the standard and find me a standard. So when on the test, when I ask you about the standard size kVA transformer, that's what I'm looking for, 30 kVA. If you put 29.6 kVA right here, that's wrong. That's your demand load. You need a standard transformer. You go next. So if everybody knows if it wasn't this, you have to go up if it's not a standard, right? Any comments, any questions guys with that? Any comments, any questions? So we got our transformer. Am I going too fast, too slow? Right speed? My numbers? Which number? Which one are you looking for?
No, just complain about it saying number 2 primary.
Primary overcap detection device, isn't that what I said on?
But you just have one over there. It doesn't matter.
So this is what you said? We're going to go find the primary.
3 things for number 1, basically. Right?
Yeah, you have to do 3 things to get number 1. You have to do 3 things to get number 1. Yeah, but ultimately, the answer for number 1 is 30 kVA. Any comments, guys? Any questions? Okay, number 2. Number 2, guys, if you look at the sheet that I gave you, number 2 says the overcap detection device, or the primary overcap detection device. Now, primary overcap detection device, what's the primary current? The current right here, 36.1. So either you get it from here, or you do the math. I like to do the math. Typical engineers, right? kVA divided by 1.73 times 480. And guess what you're going to get that with? 36.1 amps. That's it. So I could have gotten this from the table, right from the get-go. If you don't have the table, that's how you get it. It's really not rocket science. Okay. Now, we have gone to this table, so I'm not going to go there. If you guys go to table 450.3b, this is the tables where both the primary and the secondary Joe are below 600 volts. If you guys go there to size the overcap detection device right here at the primary of the transformer, remember that's the primary of the transformer. If you guys go there, it will tell you have to the primary of the transformer, and there is no, so the primary of the transformer, then you have to multiply it by what? You guys remember that? 2.5. Anybody remember the 2.5? So if you go there, you're going to have 2.5 multiplied by 36.1, and that will get you 90 amps, 90 amps. And 90 amps, I have no idea if 90 amps are a standard fuse or circuit breaker. 90 amps, you take them to 240.6, and 90 amps having to be Jeff is what? A standard, right? If it's not a standard, we go up or down? We go down. Why do you go down? Why do you go down if it's not up? Because you don't, if you guys go to the table like you have done, there is no number one. No, not number one. It's a not one.
And that one says if you go up, that's 1.25.
Yeah. Since we're missing note number one. That's a good key point. If note number one does not exist. Okay. Okay. So what's the size in this case of my fuse? The size of my fuse or circuit breaker is 90 amps. Any comments, any questions, guys? Everybody knows how to use table 450.3b. Do I need to go flash it one more time? We have been there, done that, because we did transformers. And we're using 2.5 We're using primary and secondary protection. We're using primary and secondary protection. Okay. Now my question for you is, 90. Can I go lower than 90 amps? Yes, that's a maximum. Maximum. The maximum overcapacity device. You always size the maximum overcapacity device and the minimum circuit ampacity. Maximum overcapacity device, minimum circuit ampacity. Okay. Any comments about number 2? So what do you need to do? Andrew, my friend, you go inside the panel and you stick yourself a 90 amp bolted 3-phase circuit breaker. Okay. Now let's go find the primary feeder. We need to go find the primary feeder. So for my primary feeder, my friends, the primary feeder, we need to size my primary feeder, number 3. Everybody knows what number 3 is? That's the feeder that's coming out of the transformer. So the way we do that, step number 1 is, if you guys remember, the primary current was 36.1 amps. Then what you do is you take 1.25, assuming it's continuous load, multiplied by 36.1, and that will get you a healthy 45.1 amps. Okay? So a healthy 41.5 amps. You just kind of separate these two together. All right. So that's what you do. You take the high primary, multiply by 1.25, get you 56.1 amps. Then, let me use a different color here. Then, you take the 45.1 amps to notoriously table 310.15B16 under 75-degree column, and that should get you the following. 3 conductors number 45, 3 conductors. You should come up with 3 conductors number 8 AWG, 3 conductors number 8 AWG, GHHN. GHHN. Am I right about number 8? Sounds like small, but. So based on the 45 amps, yeah, 45 amps that you're in there. Why did we go to 75-degree column even though the amps are less than 100, guys? Because it's 3-phase equipment. 3-phase equipment always rated for 75. We're no longer messing around with receptacles, and we're dealing with 3-phase equipment. So 3 conductors number 8. Is it wrong to make it number 6 for voltage drop? Or number 2 or number 4? No. The code reference directly the motors. Yeah. But 3-phase equipment, you're defaulting to 75. Any questions about this? Why 3 conductors? Why 3 not 4? It's a delta, right? We're bringing a delta. Delta Y transformers. Bring in delta Y transformers. Okay, let's go find a receptacle panel. LP low voltage. So let's go to the receptacle panel, and my LP, guys, my low voltage panel. Let me press that one. And the reason why we call it low voltage because we have a 208/120 volt. So that's what we're trying to achieve. We're trying to size the receptacle panel. Any question, guys, about the primary side? Joe, my friend, any question about the primary side? Primary side is good, right? Let's go to the secondary side. On the secondary side, guys, I have number 4. I need to size the receptacle panel. Why did I pick the receptacle panel? The size of the receptacle panel, guys, and the overcapacity device is going to decide the size of the feeder. Later on, you will see. So first, you size the receptacle panel. So I secondary, what was I secondary? So you take the 30 kVA divided by 1.73 times 208 equal 83.3 amps. Jeff, you could have skipped this and went directly into DeWalt 3-7-7, and you say, Chad, I care less about your numbers. I'm going to use this 3.8, 3.3 right from here, right? Already in the DeWalt. Okay. The second step that I do, guys, is, so here's my amps, assuming for future use, and assuming, I know these are receptacle non-continuous load. So typically, guys, they take this number and up it 25%, safety, future use, you can suspension, all this good stuff. So you take this number, what do you do with it? 1.25 multiplied by 83.3. And what would that give you, gentlemen? That we just did this math, give us 104.2 amps. 104.2 amps, right? Up it 25%. How do you justify the 25%, guys? Future expansion. It's not continuous load, though. These are non-continuous load. They're receptacle. So you design a system for what? How many years? 50 years expected life of a system that you design. So throw in 25% extra on that. And then you're going to take the last step, my friend, is you take the 104.2 amps, take it to DeWalt 3-12. That's how we size the panels. When you guys go there, it's a single phase or three-phase panel. Three-phase panel. So I have, I came up with a size 125. 125 amp. 125 amp panel. 125 amp panel. Any comments, guys? Any questions about the panel? Where did we go to find the size 3-12? On the test, other than examples, you guys can go directly to 3-12 and find me a panel board, 3-phase, and that will get me 125. Cool, 125. Any comments, any questions, guys? Finding the panel size? Now I size my panel. Any question? Going too fast? Adam, my friend? No? Too fast, too slow, too right speed? Perfect? I've been here for that for a while. Tell that to my wife, she can increase my allowance, man, so I can at least eat lunch. I can eat lunch every day instead of starving. Okay, 125. Let's go to number 5. What was number 5? Number 5 is receptacle panel overconduction device. The reason why I separate them, guys, there's a reason why I separate them, Kerry, because the panels and the overconduction device are different sizes. There are more overconduction device sizes than panel sizes. So it's a good idea to separate them. Okay, so having said that, receptacle overconduction device, what do we do? The secondary receptacle overconduction device, that will be the receptacle overconduction device and the secondary overconduction device for the transformers. What they do therein is typically They put the transformer here and the panel right next to it. So that receptacle right there acts as an overcapacity device for both the secondary and the panel. Okay? Using the tab rules. So the secondary overcapacity device. All right, so the same thing, guys, from table 450.3b, let's use the black color and let's use this. From 450.3b, you take 125 amp and you multiply that baby by 83.3, and that will get you 104.2 amps. And the 104.2 amps, take this one, this time to 240.6 and you see it 2011. If you take it there and you go to the next standard, what's the next standard? 110 amp. So your next standard is 110 amp. So I size my overcomputation device. Now, with 110 amp circuit breaker fit in a 125 amp panel, no problem. Would it be good to make the overcomputation device match the panel? Sometimes. Sometimes guys, you end up with a 600 amp panel, but your load is only 450. Do you really want to put a 600 amp circuit breaker when you need a 450? If you do that, Darren, one little problem. You have to make your conductors rated for 600 amp. So you have to ask yourself, is it a good idea? So I always get into the habit, guys, at this point, size your conductors based on the overcapacity device. Any comments, any questions about sizing the overcapacity device? So can I fit a 110 and 125 amp panel? All the time. Is it a good idea, Adam, to go make the 110, 125 because the panel is 125 since they're not far away from each other? Yes. On the test and for your friend Chad, are you guys going to do it? No. When you're in real life, you look at it as an engineer, designer, and design guys, and look, you see what I'm 110, I'm not far away from 125. I should make it easier just to stick a 125 there and call it a day. Cool? So what you did there is you went higher than the code. That's all. All right. Receptacle panel feeder, transformer secondary feeder. So the receptacle panel feeder, Aaron, my friend, and the transformer secondary feeder are the same. Everybody knows that? The secondary feeders and the panel feeders are the same. So what did they say? Match overcomputation device and call it a day. What do we need to do? Match overcomputation device, and we're going to call it a day, right? So let's go match overcomputation device. So what was the overcomputation device? 110 amp. Take this one to table 310.15 B16 and EC 2011 75-degree column, right? If you guys go there, your conductor is going to be number 2 AWGTHN. Here's my question for you. How many? You need 3 phase at least. Do we need a neutral? It's a receptacle panel. Do you need a neutral receptacle panel? I hope so, right? So you need a neutral. Do we need to derate the neutral? Guys, remember how we derate the neutral in bigger panels? Kerry, if you have a receptacle panel and panels up to 300 amp, full neutral. Full neutral. So what's my neutral? How many conductors here? 4 conductors, number 4 conductors, number 4 conductors. Why 4 conductors? 3 phase and a neutral. Why didn't I derate the neutral? Up to 300 to 400 amp, especially the receptacle panels and lighting panels, guys, full neutral is a good design. Harmonics, accommodate. So you start derating neutral really if you go higher than 300 to 400 amps. That's what starts making sense to derate neutral. Does that make sense? So we're not derating neutral at the receptacle panel, full neutral. A lot of computers, full neutral, safer. Could I have derated the neutral? Yes, if you know what the neutral load and if there's no harmonics, but there's a lot of F's, full neutral. Any comments, guys? Any questions? Any comments? Any questions? Any comments? Any questions? That's what I wanted to verify with you. Did we do? Okay, so that will be 7 and 8 then. I'll change that one. We get 7 and 8. Thank you. Any questions, any comments, guys, before I leave the transformer for good? Before I leave it, guys, I wanted to add one little thing here. I don't have room to. Okay, I think that's good enough. Any comments, any questions? So what did we do before I give you guys a quick break? Let me go back and summarize. What we did, we sized the overconduction device for the primary side of a transformer, the feeder that feeds it. We sized the transformer. We sized the feeder of the secondary feeder of the transformer that feeds the panel, the overconduction device inside the panel, and the panel itself. Gentlemen, that's what the expectation from a designer like yourself is, who does not want to be a drafter for the rest of his life, right? Any comments before we move into the next topic? I have an exam, a homework for you guys to do, and then I'm going to jump into sizing PDUs and UPS. Any question? So let me just go quick directly into the homework, and then I'll go back. Okay, here you go. So what I have, guys, for you, you have the homework. This should be homework number 7, right, Aaron? Homework number 7. Homework number 8. Okay, here's what homework number 7 is, guys. Homework number 7, I would like you to take, I have 150 kVA receptacle load, demand. Do I need, I'm giving you all the demand. Do you need to cut it by 50%? No. So the example number 7, or homework number 7 I'm giving you guys, you do not need to demand it. Yes. You don't have, I did not give you the receptacle loads. You don't have to calculate the receptacle loads and demand them. What you need to do, Joe, immediately take the 105 and size yourself a transformer directly from here. Kerry, does it make sense? No, I'm not giving you the receptacles and the multi-out assembly. You will take this one size a transformer and start sizing. Cool? Okay. Oh, yeah. You don't, here. Let me just go back. I'm giving you guys, see that demand number right here? I'm giving you that demand number right here. So I don't want you to do this step. I'm giving you that number right here. You still have to, no, I'm sorry. I'm giving you the demand right here, 29.6. This is the number I'm giving you, the demand. Okay. I'm going to give you guys 5 minutes. 5 minutes, and I'm going to go next into the UPS. Before I get into the UPS, any question guys about the receptacle? Joe, you encounter this all the time. High voltage panel, receptacle, transformer, receptacle panel. Now, for my expectation from you guys for the project that we did, please, for the project that you did, you're going to size the transformer to feed the receptacle panel exactly the same way we size it the primary and the secondary. Okay? So when we do the red lines and ask me how am I going to size this Chad, that's how I'm going to size it. The same thing, guys, the bus duct 28120, same way. When you need a transformer to feed the bus duct, right? So we'll size that transformer the same way. Okay, let's take 5 minutes break. Okay, my friend, if I can get you back, seems you guys are almost done here. Okay, here's what I have for you. If you do me a favor, Aaron, my friend, this is new topic, very important to you guys, which is UPS and PDUs. When you have a UPS, we have in our, I take the stuff that we have in our project, by the way. This is directly from our project. So let me walk you through the layout. You guys have this picture. Jeff, I do have my switch gear, the 480. From the switch gear, I'm going to take a feeder and feed my UPS system. From my UPS system, I'm going to take a feeder and feed my 2 PDUs. What is a UPS system? UPS system, guys, if you have data equipment, very important data equipment, unlike your laptops that you have. You have servers that deals with the transaction of Home Depot, Best Buy, or any of these big corporations. What they do is they have a big room full of computer crunching numbers. These numbers, if you lose the power, they need instant power, right? So what did they do? If you guys look here, they have a battery backup, and that battery will be in a battery room. Did we look at? I don't think we have seen yet a data center. We're going to be at Allianz, guys. When we go to Allianz, you're going to see they have a room full of batteries that's going to be feeding a UPS system. So here's what happens. The power comes from the switchgear into the UPS. The UPS convert it into DC and tie it to a battery system. The battery system is your backup for 50 minutes, typically 15 to 20 minutes, no more than that. Then they take it down or invert it back as into AC and transfer it into two panels. Each one of them has a transformer inside it, typically. And from these two panels, they feed it into my server. Everybody, I gave you guys this sheet. Everybody understand what's going on here? Here's my server. This is right here, the server that feeds your transaction if you're Home Depot or Best Buy or something. What they do, guys, right at the bottom, the server will have dual. You remember when what's his name? Phil. When Phil was here, and he said, if I'm the servers that they use have two plugs. One plug will be plugged in this power source. Another plug will be plugged in the other power source. When we go to Allianz, which is going to be next week or the week after, please be, you're going to be looking at these data centers and servers with dual cords, exactly like the cord that you have in the front of you, Andrew. These dual cords will be feeding the same server from two sources of power. So, one more time, here's my transaction, a crunching number type of server. I'm feeding it from two PDUs. The two PDUs in this case coming from the same UPS system. In real life, they will be coming completely from two different systems, two different substations. Okay, so if I lose power right here, the batteries will take over for 15 minutes. That will give you a safe shutdown of the system. Or a safe start to your generator. You'll be generator here, right? A safe start of your generator. 15 minutes is enough to get your generators up and running, right? These are not emergency generators. Enough to get any bugs out of the system, if any, and get your generators up and running and back up the system. So that's what we're trying to achieve. So your riser, my friend, is going to look exactly like this. If you have not done this in your riser, you have to do it. You have your switch gear feeding the UPS feeding two PDUs. We're not showing the batteries in our riser. I'm not showing the batteries. Here I showed where the batteries are, tied at the DC level. Can you see it? Typically, if you take 480 here, typically 660 volt DC here, or something similar to this. Tie them, and then you convert it back into a 480 AC, bring it into a box, a transformer and a panel, and transfer it down to 28120. Transfer it down to 28120 and dump the power across the servers. Any question about the UPS? Like I said, when we go to Allianz, guys, you're going to walk into a data center and you're going to be looking at all these servers, racks of servers plugged into two outlets like this. And then these are going through PDUs. You can see the PDUs on the walls, against the walls, and the PDUs are tied to a UPS system, and the UPS system is tied to a battery, and the whole system is fed from a feeder from the switchgear. Any comments, any questions? That's as beautiful as it can get in the electrical industry. Am I the only one who's excited today? Ouch. Huh? That's what happens when we find a job before we teach you, huh? Oh yeah, I slept really good last night. No hospital visits and so on. Okay, any question about this system? Anybody has any question there? It doesn't make sense? Jeff? Joe? Yes, no? Adam? Andrew? Because this is a new topic for us, the UPS system. Did you guys wire? Anybody wire UPS system? Okay, computer rooms and UPS system. So this is so that's what you guys are going to be doing. So what's the outcome of this exercise? When we're done here, you guys are going to do the same calculation. Do you remember when I told you leave the UPS and the PDU alone for the load calc? After we finish this, you're going to do homework for me, as well as you're going to go back and size your UPS for your building, right? The UPS and the PDUs for your building. Any comments, any questions? So what are we trying to achieve then? What are we trying to achieve? Okay, is one big box called UPS. I need to size, number one, I need to size the box, the big box that's called UPS, right? With all the electronics inside it. Number two, I need to size the overcaptation device ahead of it. Number three, I need to size the feeder that feeds that boy. Number four, where's number four? Number four, I want to go back and size the PDUs. Okay. Number five, the overcaptation device on the PDU is primary. And number six is the feeder that's going from the UPS to the PDU. From the UPS to the PDU. Any comments, any questions, guys? I will remind you the PDU and the UPS guys are bused together. The transformer and the panel for the PDU. So a PDU is nothing but a substation. It has a big fat transformer inside there and a panel and multiple panels, all bused together. They call it PDUs. Fencing in. So the primary of this panel, though, there, my friend, keep looking at you because you're looking at me. The primary of this transformer of the PDU is 480. The secondary of the PDU is what? 280. It's like having two voltages. Any comments, guys? Any question? I'm not going to leave this slide until everybody understands what PDU is. New concept for us. PDUs and UPS. I have a couple of slides, guys. Here's a UPS system. Those guys are enthusiastic famous of making UPS system. So three-phase power protection. Let me see. Here you go. So you have here's your UPS system. Different manufacturers of UPS. Different. This is APC. Makes a lot. When you do cut sheets for me, that's what you're going to be using. APC. Here's the UPS system, guys. Different product of UPS system. Different sizes. So let me go directly into one size, for example. This guy can go from 10K to 40K kVA. That little guy. Let's go to a big boys. Big boys, look at this. This can go from 400 kVA all the way to 1600 kVA. That's how you can buy them. And in modules, look at the power unity, and there's tons of information about them. Three-phase input, three-phase output. Can you guys see that? That's your UPS, three-phase input, three-phase output. So these are all different type and sizes of UPS that you can use in particular. So you can see the sizes. So to make it easier on, there's another one I want to show you, easier on you guys. I gave you some sizes. Let me show you directly here. Okay, here's how UPS looks like in the manufacturers. And you can see exactly what I drew for you. You bring the power in. Here's the DC converter rectifiers and inverters right here. Here's your battery. You go to a transformer. They call it isolation transformer. Then they dump it across that. This is the distribution part of it. And from here, Jeff, you take this one to the PDUs. That's how your UPS looks like. If you want to parallel them, they parallel them, guys. Look, they are paralleling two sets. Here's one UPS, another UPS. Excuse me. Both UPSs are paralleled into a distribution panel, and from here you can feed the PDUs. The PDUs will be right here. These two sheets are on the network for you to look at. So that's what we're sizing, basically. When we size, what I'm going to give you guys is as recommendations. Always contact the manufacturers to get you the more details. But at least if you don't have information, that's where you're going to start. All right, let's go ahead and start, huh? All right. Can I have thumbs up that everybody understands what we're trying to achieve? Shall we go achieve it? Cool, Carrie? Let's go achieve it. Okay, so let's so that's my UPS. When we go to, let's go to number one, UPS. When we size my UPS, here's the example I have, guys. I have a power factor of 80, power density 30 watt per square foot. These are the data center, these are the racks. My PDUs, I have PDU 1 and PDU 2 and UPS sitting here. That's our room. The room that I'm trying to size for is 20 by 20. So I'm sizing a room 20 by 20. I have a computer room like this room, 20 by 20. I need to put racks in it, and the power density for the servers I'm buying is 30 watt per square foot. I'm telling you, you guys, our power density in the project, do you remember, what was it, 150? 125 or 150, and we can check that. And I need to size the UPS. Here's the formula that I use. Any question, guys, before we go? So again, what you're looking at here is a room 20 by 20. I have let's assume there's two PDUs in it with a UPS. The power factor is 80. I'm going to assume power density is 30 watt. And I need to size the UPS. The first and the most important thing is to find the actual UPS size. The actual UPS size. Okay? All right, so here's what I do for the UPS size. UPS is size in kVA. It's a big box. I take the square foot of the area, or the area of the computer room or data, multiplied by the density, multiplied by 1.25, continuous load, future expansion, whatever, divided by the power factor, and 100%. That's how you get your size of your transformer. That's how you get your size of your UPS, I'm sorry, your UPS size. The square foot is 20 by 20. The density is the 30. The 1.25 is continuous load. Cool? When you guys are ready, let me start sizing. Okay, so let's go plug things into this formula. What's the square foot of this building? Square foot. 20 multiplied by 20. Why 20 by 20? Because it's 20 by 20 room. In your area, guys, remember when you took the square foot of the data center multiplied by 100, what was it, Aaron? 100, and our project was 120, the watt per square foot?
For our own project that we're working on, I forgot. You guys should remember, it's your project, right? All right. I think it's 120. Not a big deal. Really not a big deal, but
oh, 150. 150. We changed it to 150. It's 150, yep. Okay, we're sizing things to 30. All right, multiplied by, what's the power density here? 30 multiplied by 1.25, divided by power factor given is 0.8, multiplied by 1,000. Why didn't I multiply by 1,000? So I can get the actual size. And when you guys do the math on that baby, I end up with 18.8. So here, I'm going to end up with 18.8 kV and 8. 18.8 kV. 18.8 kV. So, what do I need to do? Yeah.
30, not 30.
30 per square foot. 30 watt per square foot. The square foot is here. Yeah.
I'm saying, right there, 30 watts.
Just that when you plug it in, you put 30. You don't have to do anything. Yeah, the square feet will cancel each other in the formula. I just put watt per square foot because then when you multiply by the square feet, you end up with what? Watt. So if that was 150 watt per square foot, what do you do here instead of 30? You just put 150. Same calculation. Like in your case, guys, when you calculate it, you're going to calculate it based on 150. Any question, guys? Now 18.8 kVA, before I leave this, carry one more time. No, good? Okay. So we got the square foot of the building. We have the power density. Now, you have to go find yourself an industry standard size so we can work with it, right? You can't just use this one. We need to go find ourselves an industry standard size. Okay, UPS. Did we, So, okay, so what, before that one, I need to go size find the actual size. Here's what I'm gonna find the actual size, guys, if you don't mind me putting it right in here. Okay, so I'm gonna come over here, I'm gonna take the 18.8 kVA, D12, I gave you guys a couple of sizes, 3-13. Do you guys have the sheet that you copied from DeWalt that we had? Have that sheet in front of you? Okay. If you go there to that sheet, I have a couple of sizes for you. I asked you guys to write them in 3-13, that little sheet. Adam, do you have that? Yep, that sheet. Okay, if you guys go right next to the buses, it says UPS, and the next standard that I have is what? 40. Now, in real life, what you're going to do, I gave you guys these based on one manufacturer. In real life, you're going to go and find, these are typical, what the actual size from that particular manufacturer, and then just use it. Cool? So in this case, if you go there, my size was, everybody got the size? My size, my friends, would be 40. So the size of the UPS that I'm buying is 40 kV. Any comments, any questions? So that would be step number 2 here. So step number 1, guys, is to find the actual size here. Step number 2 would be to, step number 1 is to find the kVA that you need, and number 2 is to find the actual UPS that's going to feed you, the actual UPS. Any comments, any questions? Jewel, makes sense? Okay. So now we know it's 40 kVA. The rest is history. When you capture the kVA, guys, the rest will be history, right? So number 2, I need the overcaptation device. Here's what you do. You take the 40 kVA that we've just found, divided by 1.73 times 480. Remember, my UPS is running at 480. My UPS is running at 480. That will get you 48 amps. 48 amps, right? Then you take 1.25 continuous load, 48 amps, and that will get you just 60 amps. And then you take your 60 amps, take it to the same table 310.15 B16 under 75-degree column, and I'm wrong. Take it to, thank you, to 240.6. We're sizing the overcaptation device chat, and you lose it, and you go to the 60 amps. If it's not a standard, go up, will you? Go up to the next standard. In this case, 60/60 is standard, but it wasn't the standard. If it was 61, where would you guys go? 70? We have 70? We have 70. If it was 105, where do you go? 110. Okay, so the overcam. So what do you do then? Here, you can go grab a 60 amp, 3-phase, bolted circuit breaker, and you put it in a switch gear in a panel board, and then pull a feeder from it to feed the UPS. Piece of cake. Any comments, any questions about the overcaptation device? We sized it. For our project, Andrew, my friend, you're going to do the same thing. Everything is going to be the same steps, guys, except the only difference is the size of our KVA is going to be different. Everybody understand that? So my expectation from you guys is to go back to the load calculation and size the feeders. You're going to size the feeders on the riser for me based on this step. That's why I said hold on it. When you ask me, there they said just hold your horses until we do this exam. Okay, let's go to the feeder. Let's go to the feeder. Now the UPS feeder, we're still on the primary, or still on the feeder. So you take 1.25, the same thing, guys, multiplied by 4, 8, that will give you 60 amps, same thing. So you get your 60 amps, then from 60 amps, this is where you go to table 310.15 B16, 75-degree column. And what do you get? How many conductors? You're going to get 3 conductors, and these conductors will be number 6, A, W, G, T, H, H, N, minimum. Why 3? UPS guys don't take neutral. When you bring to the UPS, you bring 3-phase. When they dump the power through the PDUs, they create their own neutral at 2.8. Okay? So I have 3 conductors, number 6. Now, Andrew, is it wrong if I go put number 2 here? No, minimum. So a lot of when Michelle guys comes here, you know what they do? If you work for an engineering firm and you're going to do all this calculation to come up with the size, you're not productive. What they do is a couple of smart guys will sit together and have a standard for the industry based on these calculations, and they have sheets. If your UPS size is this, that's our conduction device, that's a primary feeder, and that's a conduit, and it becomes an industry standard. So it gets a little bit easier. Now, what I'm hoping is you guys will be the ones who write these standards or modify them or adjust them. Okay? So you're going to find when you go, Jeff, to your company, if they said, who the idiot who told you to do number 6? Ouch. I heard. Because we're using number 2, no problem. We're doing a minimum. A lot of people get much more than a minimum because voltage drop and all this stuff. They up it one size just for voltage drop. Okay, so we got that one. Any questions about the minimum size? Minimum size. Okay, so we sized the overconduction device, and we sized the feeder for the UPS. The next that we need to size, guys, is the PDUs, power distribution units. Power distribution units. Power distribution units. Exactly the same formula. We use the same formula, exactly the same formula that we use for the UPS. Same formula, right? Square foot multiplied by the density, multiplied by 1.25, divide power factor, and 1,000. Okay, so I'm going to repeat myself here, so excuse my repeating. So I'm going to go right in here, guys, and say KVA for this project will be 20 multiplied by 20, that's the square foot of the building, multiplied by 30, multiplied by 1.25, divided by 0.8 times 1,000. And if you guys came up with same thing, 18, I came up with 18.8. Okay, let's write it down somewhere where we can. Multiplied by 1.25 equal 18.8 kVA. Same size like the UPS, same size. Then what we're going to do, guys, is we're going to take the same thing, 18.8 kVA, take it to Chad's sheet that I gave you, deep walled under 3-13, and that will get you a size of 40. Now, always, PDU sizes, guys, sometimes are different. The reason why I gave you guys, Jeff, the reason why I'm referring you to the sheet that I gave you just for standards, you're going to go find the industry standard for the PDUs. It might be 50 the next standard. But for the ease of installation for us, I'm referring you to the same UPS and PDU sizes. Okay? The actual size would be different. When you take 18.8 kVA, they might not make 40 kVA PDUs, they make them in standard of 30. You know what I mean? 60. That's the only difference. You're absolutely right. If you use the same formula, you should come up with the same answer. Absolutely. I used to, then the manufacturer got bought by another manufacturer, and it's really hard to keep track of them right now. Just for the sake of standardization, I just start giving the students these numbers and use them at least. Just to standardize for the test, because I don't want everybody going to different manufacturer, come up with different size. But if you have a PDU, the first thing you need to do is to go to one manufacturer, look at the actual PDUs that they use, and then that's part of you project management skills is to find the next standard and stick it right here. But in school, we're only interested in the process. What's the difference there in if you went to ABC right now and find that the standard was 50? What's the difference in terms of continuing with the calculation? Nothing. Just the number will be different. Does that make sense? They're close to the standards, the one that I gave you, but they change so much when you get bought and all this good stuff.
The KVAs are also mostly the same, just the size.
The size. It's like panels and circuit breakers. They don't make them in the same size. You know, there's so many sizes in circuit breakers, but smaller size, a smaller number of sizes of panels. Okay, so we have 4. What do we need to do then? We got the size. We're done here. We size our PDU. By the way, if you have 2 PDUs, do you cut the load by half? No, PDUs are redundancy. So that 40 kVA, there will be 2 of them. So the idea is, if one of them is faulted, the electronics screwed up in one of them, the load will be shifted directly to the second one, and the second one should be, one of them should be able to handle the load. So under normal operating condition, Joe, they will be carrying 50% of the load. 50% of the load. Normal operating condition. Okay, PDU, overcompression device. I want to remind you guys the PDU, what does the PDU has inside it? There's a transformer inside the PDU. There is a transformer inside the PDU because it takes the 480 right here, it takes the 480 down to 280. And all in one big box. There is a transformer inside it. So what I would do, because there is a transformer inside it, I would use the transformer rules, my friends. So let's go find the full load current here. Here's my 40K divided by 40K divided by 1.73 times, remember, we're still on the primary side, so we're still 480. And that will give me exactly what we got before. This amps, right? 48, we got this. Now, because we have a transformer ahead of it, 450.3p, guys, allows you, because we have a transformer, allows you to use this guy, 450.3p. So then you take 2.5, I check 2.5 multiplied by 48, 2.5 multiplied by 48 equal, I'm coming in a second here, give me 1 second, but 120 amp. And this number is coming from 450.3b, the table, 450.3b. Okay, and then if it's not a standard, then you take the 120, multiply it, you take the 120, take this one to 240.6 and EC, and you go down if it's not a standard, so your standard amp is going to be like this. Okay, Aaron, what's up?
No, I was about to ask why it ran 480, but then I just realized that the PDU is a transformer.
Yeah, there's a transformer inside them. That's kind of the weird thing. The primary transformer, the secondary is bussed in. We don't even size it. We're really sizing this guy. The secondary, you don't even get involved in sizing it. It's already sized by the manufacturer. Based on the size of the PDU. When you tell them 40 kVA PDU, they come up with the size of the panel that comes with it, and they don't even, typically they add into it. We're really just sizing the feeder that feeds it. That's all. One more time. The reason why I put the 480, even though we have the PDUs, guys, because we're sizing the overcompression device ahead of it. Actually, in reality, the overcompression device will be right in here. That's how it goes. So that's the one that we're sizing. That's the one 110 amps. That's what we're sizing. That's coming to the PDU. This one on the secondary side, Jeff, is already done by the manufacturer. It's one big box. Cool?
Is there any computers that run on any 720?
Yeah, 2.8. They use a lot of 2. No, they either they have two hots and put them across the server and burn them at 208, or
Computers are running at 208 volts.
yes, well, they convert it to DC, yeah, but they take power at 208. Yeah, they have servers that run at 208, single phase though, 2 hots, or 120. But either way, in this case, if it runs at 208, what do? You take two circuits, a plug, there will be a 208 plug, just 208 with a ground, and you wire a plug, and you plug the server in the 208. If it's 120, no problem, a neutral and a ground, ungrounded conductor, grounded conductor, and an equivalent conductor, and you plug with the 120. Okay, the last thing we're going to size, my friends, the last thing, see how easy that is? Piece of cake. Isn't that a piece of cake? Am I the only one who's excited? No? All right, so the last thing is the PDU feeder. So what I would do, guys, I take 480 amps. These are my input to the PDU, right? And you multiply 1.25, add it, because assume it's going to be continuously running. Multiplied by times 4, 8, equal. When you go there and get your 60 amp, okay? And then, my friends, you take your 60 amps, don't forget to take it to 310.15 B16, 75-degree column, and that will get you 3 conductors, number 6, AWG. And I'm sure some of you said, didn't we write this a second ago, Chad, for the UPS? Absolutely. And the PDU is going to be the same. As long as the actual sizes of the KVA are the same. Almost always, guys, the PDUs, well, you can have multiple PDUs from the same feeder, though. Yeah, in this case, if we have 1 PDU per UPS or 2 PDUs per UPS, it'll be the same size. No. Typically what they do, guys, is they have 1 PDU here, 1 PDU here. They're fed from 2 separate UPSs that's fed from 2 separate panels that goes all the way to the service, and the service is fed by multiple generators. That's how they do it. In our project, the calculation wouldn't change. In our project, guys, just for the ease, we give you 1 UPS with 1 PDU. But we want the 2 PDUs to be, we want the 2 PDUs to be the same size. So if one of them is to crap on you, you just shift the load. You don't have to, because your servers are plugged in, both of them. So if that PDU is shut down, your server continues to run. Any comments, any questions, guys? Any comments, any questions? Now, Andrew and Darren, is this enough for you guys to size a PDU for your project? Andrew, cool. Kerry, my friend, and Aaron, are you guys, is this enough to size your PDUs? Adam and Joe, good? Jeff and Zach? Okay. That's what I thought. Wait a little bit until we go over this. Okay, so what we did, just to summarize, guys, we sized, go back again, and I'll, so what did we do? We sized overcomputation device for the feeder that feeds the UPS. We went and we sized overcomputation device for the PDU, as well as the feeder that feeds the PDU. Now the question would be, what happened, Chad, to the secondary side, the 208 one side? This is sized by the manufacturers. It's 1 box. You're bringing a 480 feeder to it. The beauty of this one, Andrew, my friend, is they take a big chunk of 480 all the way from floor 1 to floor, say 5, and they put the PDUs, guys, where the data center, which is located in the say the 5th floor, and then you don't lose voltage because you're using 480. So last thing. Your UPS is going to be 480. Your PDU will be a 480, but it will be also it has transformer inside it, 28120. When you drop the PDUs, guys, on in our project, it's going to have 2 connectors. One of them says 208, and one says 480. I'll show you that one when we start doing power. Last thing, homework. This is what I have for you guys for homework. Please, homework number 7 and homework number 8. We talked about homework number 7, the demand load. You have to size a low voltage panel and transformer, receptacle panel. For homework number 8, we have a 30 by 30 computer room. The power density is 100 watt per square foot. I will emphasize, Zach, that these are done separately, not as a team, guys. When you do them separately, right? Cool. Any comments, any questions about the homework? Cool. Any questions about what we covered? Does it make sense? So I picked these guys specifically because related to what we do. Now we move on. Our next head, guys, will be grounding and bonding, detailed grounding and bonding. And then we will go, the week after, we'll do fire pumps and a couple of other things. Cool? Any comments, any questions? Aaron, makes sense? Okay. That's all we have. We'll do red lines. Thank you.